So in this lecture, we'll continue talking about the law of reflection, and we'll mainly discuss the law of refraction. And in particular, we'll talk about Snell's law and some of its consequences. So this has to do with how light bends as it moves from one medium to another medium, where the speed of light changes inside the medium. And of course, that's encoded in the index of refraction, which is the ratio of the speed of light in vacuum to the speed of light inside the material. So last time we started talking about the ray model of light. So basically, for any object, let's say a tree, the idea of the ray model is that from every point on this object, we can imagine these rays that are emitted from every point and move along straight lines. And we talked about reflection. So what happens when these rays hit a flat mirror-like surface, a highly reflective surface? Well, if they hit it at some angled theta incident, so the angle the ray forms with the normal to that surface, the law of reflection is really simple. It's just the reflected ray makes the same angle. And we talked about a simple consequence of this was that there's going to be a virtual image, right? So if you have some object in front of a mirror, what you see when you look at the mirror and these reflected rays come toward your eye, it's like they're coming from an image behind the mirror that's the same distance. So S is equal to S prime from the mirror. And that's just a direct consequence of this law of reflection. If the angles are the same, so consider, one particular ray going this way getting reflected. If these angles are the same, all these rays, if you trace them back behind the mirror, it looks like they're coming from the image of that point. And that's true for every point belonging to this object. And this image is called a virtual image because really there's no light converging there. Physically, there's nothing, right? That's behind the mirror, and let's say there's a wall there. So there's no light there. It's just the light lives over here, right? These are the reflected rays. So there's nothing behind the mirror. Just if you trace them back into this place where there is no light, they converge at one point. So that's not a real image, that's a virtual image. Anyway, so we talked a little bit about this. We looked at some scenarios, like so we had one example where you have a light bulb and you wanted to see like how big is the reflection on the ground when you have some vertical mirror. So basically we looked at the reflected rays from the two ends of the mirror, and anything in between again ends up in this bright spot. Okay, so let's take a look at one more example to practice a little bit more, and then we switch to the new topic for today. Okay, so here's a problem. So your height is h. What is the shortest mirror on the wall in which you can see your full image? And where must the top of the mirror be hung? So yeah, so pause the video, try to figure this out. You can also assume there's some length between your eyes to the top of your head. So your height is h, and let's say the distance between your eyes and the top of your head is L1. Okay? So in terms of these, try to figure out the solution. All right, so let's go back to the notes. Let's see, this was example 34-2. Okay, so let's say there's a wall here and we want to hang a mirror on this wall. And here is the floor. Okay, so then this is a person, let's say it's you. And then your eyes are somewhere here, right? So your height is h, so from here to here we have a height h, and then let's say there's a distance L1 between your eyes and the top of your head. Okay, so in order for you to see, right, your entire body in the mirror, for every point belonging to your image, there should be a ray that can reach your eye going through the mirror, right? So that's a simple way to think about this. So if I, let's say, consider the image on this side, right, that's the image. So the ray from the bottom of the image, it should be able to reach your eye. So if I draw a line from the bottom of the image to your eye, the bottom of the mirror cannot be above this point, right, where that ray kind of hits the wall. And again, from the top of the image, if I draw a line to your eye, okay, it hits the wall at some point. Again, the top of the mirror cannot be below that point, right? Because if it's below that point, this ray cannot reach your eye. It's not going to be reflected among the rays reflected from the mirror. So this really gives us a constraint of where the mirror should be, right? It gives us the top and bottom. And if it's bigger, fine. I mean, if the top goes above this point, fine. Or the bottom goes below this, fine. But if it gets slightly shorter, so for example, if the bottom is here, you're not going to see your feet, right? If the bottom is at some point over here, the lowest point of the image you can see is somewhere over there, for example. All right, so then just let's look at this triangle. So from the eye to the top of the image to the bottom of the image. Okay, so I'm drawing this big triangle here. From the eye to the top of the image and to the bottom of the image. Okay, so we know that, let's say the wall containing the mirror is over here. So we know that the distance between you and the mirror, let's call it S, is the same as the distance between the mirror and the image. That's also S. So these are all similar triangles, right? And then if you consider this triangle, let me show it in red here. It's going to be a similar triangle as the big one, and all the dimensions are half, right? So the line kind of perpendicular from this vertex to this side, I guess it's called the altitude, here has a length s, in this case has a length 2s, and all the angles are the same, like this line is parallel, like the wall is vertical, your image is vertical. So yeah, so the red one and the big black triangle, they're similar triangles. So one has dimensions that's twice the other. So then if this has a side h from here to here, I must have h over 2. And yeah, so that's the minimum height of the mirror, right? If we place it in the right place, that's the minimum height it should have. So if, yeah. And then what is that right place where, well, we know that if this is the image of the top of your head, so that's the top of your head, this is your eye here. So that distance we called L1. Therefore, again, now this triangle is similar to this triangle. So here I should have L1 over 2. And yeah, so that's where it should be. So it should have a height that's h over 2, half of your height, independent of the distance between your eyes and the top of your head, but we should hang it in the right place. So if the top is slightly below that point, we're not gonna see the image of the top of your head. And if the bottom is slightly above this point, again, we're not gonna see the image of your feet. You can also think about just the law of reflection without kind of directly thinking about the image. So one way to do that is, let's say, consider again this. So let's say that's top of head, and this is the eye. That's the mirror. So if the ray from the top of your head hits the top of the mirror and reaches your eye, which it should, right? That determines where the top of the mirror should be. Well, it's going to look like this. So if you think about the normal, these two angles are the same, theta, theta. So that means that this length is the same as that, right? This is going to be, let's say that your distance is s, right? This horizontal distance here is s. So this is s tangent theta. This is also s tangent theta. So they're the same distance. And then if their sum is L1, which is the distance between the top of your head and your eye, then that should be L1 over 2. And similarly, one can argue that, again, we can play the same game, except instead of the top of your head, you think about your feet, and then, again, like if this distance is L2, right, the bottom of the mirror should be L2 over 2, right, for the same reason, because if this is alpha, and then each of these heights become L2 over 2. And then the height of the mirror becomes L1 over 2 from here, plus L2 over 2. L1 plus L2 is h, so the answer becomes independent of h. All right, so let's take a look at the solution. Yeah, it seems the book is doing it the second way. So exactly the second argument that we gave. Okay. All right, so now let's talk about refraction. So you have, so this is I guess a prism. Yeah, so a piece of glass with some triangular shape. And then you have a beam that's incident on this. Of course, always what happens is part of it gets reflected. So that's the reflected ray. And part of it goes through. Now, refraction means that the light bends as it moves. So the direction of this ray changes as it enters this new medium where there's a different speed of propagation. So how can we make sense of this? Well, again, in the same way that we thought about the wavefronts, and we figured out that the angle of the incident light must be the same as the angle of the reflected. We can again think about the wavefronts, right? So let's say that's the beam. Let's say we have some angle like that. That's theta 1. So those are the beams. Those are the rays, sorry. And then we can think about the wavefronts associated with that. So let me draw now the wavefronts. The wavefronts are going to be perpendicular to the rays, right? And are separated by the wavelength. So here are these wavefronts. And let's say the wavelength in this material on this side, on the top side, let's call it lambda 1. And this angle is theta 1. And this is the same angle, right, between the ray and the normal to the interface is the same angle, theta 1, between the wavefront and the interface. So the wavefronts are perpendicular to the rays. This normal is perpendicular to the interface. So if you take, the normal and one of these wavefronts and rotate them by 190 degrees, the normal rotate them by 90 degrees. The normal coincides with the interface, and then the rays coincides with the wavefront. So it's going to be the same angle. And then, so see, let's say the wavefronts are kind of the crests in the electric field of this electromagnetic wave. So you're going to have a crest in both materials. They should coincide. So where you have a wavefront here, they just continue and can bend when they enter the other material. So let's say they kind of look like this. They go a little bit this way. They're perpendicular to these rays. Now this angle must be theta 2 here. Theta 2, theta 1, theta 1. And now the distance between the wavefronts in this second medium, second material, let's call it lambda 2. Okay, so let me draw a slightly better picture with just two wavefronts. So again, I have the interface, I have one wavefront here, I have the next wavefront here, theta 1, theta 1, these are two parallel lines. The distance between them is lambda 1, the wavelength over here. And then you get theta 2, theta 2. The distance between them is lambda 2. Okay. So then we see from this representation that the angles and the wavelengths are not independent. An easy way to see this is considering two right triangles. So let me consider one right triangle here. So we go perpendicular to the wavefronts. So that's one right triangle shown in blue. And I can consider another right triangle over here. Okay. So these two right triangles share a hypotenuse, right? So this side they have this side in common, which is the hypotenuse. It's opposite the 90-degree angle in both of them. So let's call the length of the hypotenuse L. And now from here to here, I have lambda 1, right? That's normal to the wavefronts. From here to here, I have lambda 2. So the equations I can write are lambda 1 is opposite an angle theta 1. So it's going to be L sine theta 1. Lambda 2 similarly is opposite this angle theta 2. So it's L sine theta 2. Okay, so we didn't know what the hypotenuse was, but we can just eliminate it and get the ratio lambda 1 to lambda 2 to be equal to sine theta 1 over sine theta 2. Now, remember what happened when waves propagated from one medium to another. The frequency was a property of the source. It doesn't change. But if the speed changes, the wavelength has to change. So we can write lambda 1 is v1, the speed over here, divided by the frequency of the light. Lambda 2 is v2, the speed on this side, on the bottom side, divided by the frequency of the light. They have the same frequency. So this gives me that lambda 1 over lambda 2 is v1 over v2. And the ratio of the speeds we can relate to the ratio of the indices of refraction, right? Remember, n, the index of refraction, was defined as the ratio of the speed of light in vacuum divided by the speed of light in some materials. So we can write it for both of these materials. And these two give me v1 over v2 is equal to n2 over n1, right? They're inversely proportional. Okay, so these three equations, lambda 1 over lambda, so sine theta 1 over sine theta 2 is lambda 1 over lambda 2, which is v1 over v2, which is n2 over n1. So then we can write sine theta 1 over sine theta 2 is n2 over n1. Okay, so now we can just forget about the wavefronts, we can forget about the wavelength, just go back to this geometric approach to the rays, and we arrived at the so-called Snell's law, which tells us how a ray bends as it propagates from one medium to another. So let's say the index of refraction here is n1, here it's n2. This is normal. You have a ray at some incident angle theta 1, and let's say, I don't know, there you have air or something like that, and here you have a piece of glass or water or some other transparent material where you have an index of refraction that's larger than 1. So let's say n2, for example, is larger than n1. So if that equation is satisfied, sine of theta 1 must be larger than sine of theta 2, so theta 2 must get smaller. So this ray kind of bends and gets closer to the normal. So as it enters a material where the speed goes down or the index of refraction goes up, the ray bends in a way that it gets closer to the normal, to the interface between the two materials. So here we have theta 2. And another way to write this equation is we can kind of multiply them, right? n1 times sine theta 1. It's a more common way to write it. It's equal to n2 times sine theta 2. So that's known as the law of refraction, or Snell's law. All right, so that's a better picture, right? Just showing the Snell's law. One thing that's important to remember is that these angles are defined with respect to the normal to the interface. So if we apply this formula, we have to remember that it's not the angle between the ray and the interface, it's the angle between the ray and the line that's normal to the interface. All right. It also works the other way. So you can think about the reversed ray. So there was nothing special about medium 1 or medium 2, right? So if you have incident ray this way, you form angle theta 2. Inside medium 2, you're gonna get the same angle theta 1. So the relationship is the same. And as usual, part of the wave goes through. So part of the wave goes through. So this ray that gets traced, this is the part that goes through, and there's always some amount that gets reflected from the interface. Okay. Yeah, so that's some samples of indices of refraction, and this is basically the connection with the wavefronts that allows us to derive Snell's law. All right, so here's a quick question. Pause the video, try to figure out the answer. All right, so you have a ray of light passing from medium 1 to medium 2, and it's refracted like that. So what can we say about N1 and N2? Well, it's moving away, right, from the normal. So the angle with the normal increases as we pass from one medium to the other. So here, let's say the angle with the normal is theta 1. Here we have theta 2. So that implies that sine of theta 2 is larger, so N2 must be smaller. Right, it bends away from the normal, so it's entering a medium with a smaller index of refraction. All right, so here's a problem. So yeah, try to read through this, pause the video, work through this problem, this example to the very end. It's a very useful problem to get some practice with refraction and Snell's law. And then we come back and work through it together. All right, so I hope you figured it out. Let's see. So you have a prism. These are the angles, 30 degrees, 90 degrees, 60 degrees. You have a laser beam that enters the prism. It's initially normal to this interface, so it just goes through. And then when it leaves the prism, it makes an angle of 22.6 degrees with the horizontal line. All right, so, and the problem is asking us to find the index of refraction of the prism. We can assume that outside in air, the index of refraction is basically 1. So example 34.4. Let's go back to the notes and try to work it out. Okay, so we have a prism, looks like this. 60 degrees, 30 degrees. Here is 90 degrees. You have this ray. Well, here the incident angle is 0, right? So if you want to think about refraction here, theta 1 is 0. So n theta 1 is 0, therefore n theta 2 must be 0, so it means theta 2 is 0. So a ray that's normal to an interface doesn't bend, it just goes through. Both angles are 0. So this goes through straight ahead. Then it hits the second interface. Okay, and then it bends. So here, let's say we have n. And outside, the index of refraction is 1. Okay, so what we know is the angle with this horizontal line. I believe that was 22.6 degrees, maybe? Okay, so Snell's law tells us about signs of the angles between the rays and the normal to the interface. So let me draw this line that's normal to the interface, right? Okay, so the angle on this side, let's call it theta 1. So what is that angle? Well, here I have 60 degrees, right? And this is 90 degrees if I draw a normal to the interface, so that must be 30 degrees. What about the angle on this side between the ray and the normal? Let's call that theta 2. So theta 2 is going to be the same 30 degrees, right? This part is 30 plus the angle given between the ray and the horizontal, so it's going to be 52.6 degrees. And n2 is 1, n1 is n, the index of refraction we want to find, the index of refraction of the material of the prism. Okay, so we can write sine theta 1, n1 is n2 sine theta 2, so that means n1 is n sine 30 degrees, n2 is 1, that's air, sine 52.6 degrees. Therefore, n becomes sine of 52.6 degrees divided by sine 30. Sine 30 is 1/2, so that's 2 sine 52.6, and let's see what that is. All right, so yeah. Yeah, so whatever it is, the answer turns out to be 1.59. So sine of 52.6 divided by sine of 30 is the index of refraction of this material. Okay, so you can also try to find it in the table, and it seems it's some kind of plastic. All right, so now, so kind of our assumption in deriving Snell's law was that the wave is able to propagate, right, in both of these materials. But so suppose you have n1 and theta 1, right? And you shine this laser at the interface or on the interface. So so then suppose n2 is much, much smaller than n1. So the light will want to bend away from the normal, right? But if it's entering the second material, the angle with the normal cannot be larger than 90 degrees. So we may not have a solution to our problem, right? So let me elaborate a little bit on this. So we're talking about total internal reflection, where light just cannot go through. All of it has to get reflected because there's no solution for the direction of transmitted rays. So let's say consider n2 smaller than n1. Okay, so let's say here we have n1, here we have n2. And then you shine light at some angle, theta 1 here. And then you're going to get a bigger angle, theta 2 over here. So now we're saying sine theta 2 is n1 sine theta 1 divided by n2, right? So now let's say that's the incident, and then we want to solve for theta 2. But if the ratio is too big, right, n2 is smaller than n1, so n1 over n2 can be a large number. So it could be that this side of the equation becomes a number that's larger than 1. But then we want to find the angle whose sine is a number larger than 1, and there's not going to be any solution. So there's some critical angle, right, where theta 2 becomes 90 degrees and its sine is 1. And then if your theta 1 gets larger, then nothing goes through. The entire wave has to get reflected. So let's say, consider this case. Let's say that's theta critical. This is n1, n2, such that theta 2 is pi over 2. Okay, so in this case, what is the equation we would write? We would write sine pi over 2, which is 1, is equal to n1 over n2 sine theta 1. And that means sine theta critical, we called it, is n2 over n1. Yeah, so n2 over n1 is a number that's smaller than 1. So there's going to be some angle like that, some angle to theta critical. So now if we're kind of closer to the normal than this angle, we're fine because sine of theta 1 is going to be smaller. And then we can find the solution here. But if sine of theta 1 is larger than sine of theta critical, so if you're incident at some larger angle, therefore its sine is larger than n2 over n1, but it's multiplying n1 over n2, so it's going to give a number that's larger than 1. There's no solution for theta 2. So the lesson is, when your incident from an interface with a high index of refraction from a medium with a high index of refraction onto a medium with a smaller index of refraction, such that you bend away from the normal, there's going to be a critical angle given by this equation. Let's say arc sine of n2 over n1 such that if your incident angle with the normal is larger than that, nothing goes through. You're going to get total reflection. Okay, so that's an important observation, right? The Snell's law, we can write it, but it may not have, I mean, it does not have solution in certain scenarios. If n2 is smaller than n1 and your incident angle is too large, the entire thing gets reflected, and we can find this critical angle by just looking at the case where theta 2 is pi over 2, so that critical value, it's really not transmitted, right? It's just bent so much that it's tangent to the interface. All right. Yeah, so that's a nice picture describing what we were discussing. So we have N1, let's say it's water or glass or something. Say it's water and you have a flashlight underwater. And here you have air, so N1 for water is larger than N2 outside. Yeah, the normal one goes through, then at some small angle, yeah, it bends away from the normal, goes through. Some of it always gets reflected. And then there's this critical angle where kind of what goes through is parallel to the interface. And then if you have an even larger angle, theta 1 larger than theta c, that's critical value, the entire thing gets reflected. Nothing can go through. And mathematically, this ties in with Snell's law not having a solution for theta 2. And this phenomenon is called total internal reflection. Okay. So here's a quick question. Read through this, pause the video, try to figure out the answer. All right, so let's see. So we have a beam that undergoes 2 refraction plus total internal reflection at the interface between medium 2 and 3. All right, so it's incident here. At this interface, it bends away from the normal. At this interface, it doesn't go through. It experiences total internal reflection. Comes back, bends toward the normal, enters medium with N1. Okay, so which one is true? So first, part A is saying N1 is smaller than N3. B is saying N1 is larger than N3. C says there's not enough information. So what do we know? What are the things that happen? Well, here we're getting total internal reflection, which means N3 must be smaller than N2, right? Because if N3 is larger, you want to bend toward the normal as you reach here, and then you can enter. But if N3 is smaller, you want to bend away from the normal, so you may not bend away. You may not be able to bend away enough because the maximum is 90 degrees. So we know N3 is smaller than N2. Okay, so let's write it here. Right, you would get total internal reflection if the tendency is to bend away from the normal. So here, how can we compare N1 and N2? Well, we know that as you enter from 1 into 2, you bend away from the normal. So N2 again must be smaller than N1. Right? Yeah, theta 2 is larger than theta 1. Sine theta 2 is larger than sine theta 1. So Snell's law implies that n2 must be smaller. So it seems now we know n3 is smaller than n2 and n2 is smaller than n1. So combining these means that n3 must be smaller than n1. And yeah, and B is the correct answer. Okay. So here's another example. So we have a light bulb in the bottom of a 3-meter deep swimming pool. And we want to see what is the diameter of the circle of light seen on the water surface from above. Okay, so we want to use the ray model of light. See that there are these rays right from the light bulb. They go in all directions. But if they're going this way, air has a smaller index of refraction, so there's going to be some critical angle for which no light comes out. Everything gets reflected back into the water. So we're going to see this bright circle when some light comes out of the water and enters the air. So to find the diameter, we need to find that critical angle, theta c, for which the refracted ray is just parallel to the interface. The angle theta 2 is 90 degrees. Alright, so that's easy, right? So we can write theta critical here. We know n1 times sine theta critical is n2, which is 1, times sine of 90 degrees, which is 1. So sine theta critical becomes 1 over, n2 is 1, n1 is 1.33. Okay, so we have that angle. And then how do we find the diameter? Well, we can focus on this triangle here, right? We know the height, we know this side has a length h. So if I call this r, which is half of the diameter, right? D is 2r. Then I know tangent theta critical is r over h. So r is just h tangent theta critical. So D becomes 2h tangent theta critical. And we already found theta critical. We found its sine, so you can take the arc sine and and then find its tangent. This looks like, what does it look like? So it's roughly 3 over 4, I think, right? So yeah, so if I want to get this angle without using the arc sine function of my calculator, which is probably the better way to do it, I guess we can just visualize that triangle. So we're saying sine is 3 over 4. So if this is 3, this is 4. This side should be the square root of 16 minus 9. So it's like square root of 7. And then tangent of theta critical should be 3 over square root 7. So D should become 2 times 3 meters times 3 over square root 7. That's in meters. So 18 over square root 7 meters. All right. Yeah. Yeah, so theta critical is arc sine of 1 over 1.33, and we can find the angle, find its tangent. So, yeah, I think it's close to 18 over square root 7. All right, so that's a good place to stop. We'll continue the discussion of ray optics. Next time we'll talk about curved interfaces, kind of curved lenses and mirrors, etc.